Now, the very first model we're going to look at is a coordinated turn. Now, this is not a linear model, but what it does do is allow us to design trajectories about which we can linearize. So, to give you an idea of what the coordinated turn is, I've brought my little toy plane in here. And an aircraft has two different ways that it can turn. First, we can turn our rudder. So turning that back and forth. If we turn our rudder, then we'll end up doing what's called a skid to turn. Now, a skid to turn is quite undesirable for an aircraft, as is in this rotating motion, it's going to cause all the passengers, if you're in the aircraft, it's going to cause your passengers to smack their head on the sidewall, right? So it's uncomfortable for passengers, but also for aircraft, it's going to give us a larger side slip angle. So as we'll end up skidding to turn, we'll end up having our nose pointed away from the direction of travel. So instead, what we can do is a bank to turn. So again, looking at our aircraft, we have our ailerons that we can move, and our ailerons cause a rolling motion, and this rolling motion will cause us to turn. So what we do is we create a rolling motion, and we turn, and we go basically in a circular motion. So it's a really fantastic way to turn. Then when we do that, all of the forces are going out the ground, and it's much more comfortable for passengers. Allows us also to keep a small slide slip angle. Side slip. So anyway, let's go ahead and get started. So we're going to jump in, and we'll start to look first at this coordinated turn if there's no wind and we're doing level flight. So we're not trying to increase our altitude, we're trying to maintain our altitude constant, and this provides a slightly simpler formulation. So again, I'm going to write up here, we have our goal is we want to bank to turn instead of skid to turn. And ideally, we'd like to go, we're going to develop the what needs to happen for us to go in a pure circular motion. So looking from a top-down view, we can see here's our center. That's our center of rotation. And we want to act as if we have a string attached to the aircraft, and the aircraft is just moving around in that circle. So what we need to do in order for that to happen is we need to balance forces to make it so that we stay on that circle. So let me write that down. Our approach is we're going to balance forces. So assuming our aircraft is in the desired state, we got to make sure that our forces are balanced. So now, as we're moving around in a circular motion, well, our aircraft will experience what's typically referred to as a centrifugal force. And that force, if you've ever been on like something that's spinning, you feel like you're getting pushed out. And that force can be modeled as your mass times the velocity squared all over the radius of that circle that you're traveling in. So this is, again, it's the force. It's a force felt by the rotating motion. And we can look to see what V is. If we look at V, that's just our velocity. And so in the no wind condition, what this is going to be is just, it's going to be VA. We can also look at V and a relationship between the rotating motion and the radius at which you're traveling. And we can write this, so this is also equal to R times omega, where omega is our rotational velocity. In this case, if we look at where we're going, our rotational velocity is going to be the time derivative of our yaw angle. So we'll say this is equal to r times our psi dot. Okay, so we'll use one interpretation each. So we have this v squared term. We're going to use one interpretation each for defining that force. So this force is going to be equal to mass times VA times our psi dot, I almost put omega, all over r. So those r's cancel out, and we end up getting this term right here. So that's the force pulling us out of the circle. Okay, so we have that centrifugal force pushing us out of the circle. We want to balance that with our lift force. So if we look at our lift, so here's just looking straight into the nose of the aircraft, the lift is going to be pointing in a direction perpendicular to the wings of the aircraft. And we can look at that and we can say that, hey, let's figure out what is our lift going up. So it's going to be F lift, and we have the angle between it, so it's going to, the closer one is going to be our sine of phi. Cosine of phi, sorry. Cosine of phi. And the component going in the horizontal direction is going to be F lift sine of phi. Okay. So looking at that, we have our lift, and we've just decomposed it in terms of the role of our aircraft. So coming back over here, we have F lift sine of phi pointing in towards the center of the circle. And so what we really need to do is have those balanced. So we need to have the F lift sine of phi is equal to m times VA times the time derivative of psi. Excellent. Now we also have, in this figure, we can see it really easily, we have our gravity force pulling us down, and we have our lift force pushing us up, but it's not our full lift force, it's a lift times the cosine of phi, right? And so we have this other equation that we want to balance. So in this side, we're balancing this with the centrifugal force. And in this side, we're balancing, oops, can't write, with gravity. Gravide. There we go. Gravity. All right, so what we're going to do is we're going to divide one by the other. So what we do is we say we have F lift times the sine of phi is equal to mVA psi dot. And we're just going to divide both sides by F by our vertical force, F lift cosine phi, and that's just equal to, we have mg. All right, so our F's cancel out, our M's cancel out. This guy right here, sine over cosine, is just our tangent of phi. So we have the tangent phi is equal to VA psi dot all over our gravity constant, and solving for our psi dot gives us this equation down here. So we have our psi dot is equal to the gravity over VA over our airspeed times the tangent of phi. So if we're doing that, then if we have psi dot equal to g over VA tangent of phi, then we'll be moving in that circular motion. So now if we want to go to our full coordinated turn model, we can apply some of the same principles, right? So in our goal, we still want to move around of a circle. So we want to move around a circle of radius r. But now we're going to allow ourselves to do two things. One, we can have a non-zero angle of attack. And having a non-zero angle of attack will allow us to move upwards vertically. So we're basically twisting around as we're coming up, spiraling up. The second thing we can do is allow wind, which if we allow wind, we're going to be looking at our course angle instead of just our heading angle. So if we now look at the aircraft from top down, we may be pointed in some direction. So this direction, this direction would be coming out the nose of the aircraft. If we were to look at from north down, that was our heading angle. But we might actually be traveling in this direction. So we'll be traveling in that direction. In that case, recall that's going to be our course angle. Okay, so we were to draw this, we still want our course angle to be tangent to the circle. So we're traveling around still in a circular motion. But now we're just going to be looking at our course angle instead of our heading angle. So this is a top-down view. If we look at more of a side view, we can look to see that, say we have our aircraft, beautiful aircraft. We have where out the nose of our aircraft, where that heading is. In this case, it'd be we're looking at our pitch. And then we have our V sub G. So where we're actually moving. So if we look at this guy, this would be our pitch angle. This guy right here is going to be our angle of attack. Whoop. Okay, it's going to be gamma. Okay, so if we do that, and I have to apologize, I keep calling gamma my angle of attack. Gamma is, again, our flight path angle. Okay. So looking at it from the side, we can see that we're traveling upwards. Now we're not traveling at the angle of theta, but we're traveling at the angle of gamma. So from the side view, we can calculate what is our airspeed in the horizontal direction, right? So given gamma, and we know that that's the angle from the horizontal to V sub G, what we can do is we can say that I'll draw it in red, this component of the horizontal component is just going to be our Vg times our cosine of gamma. So now we have that horizontal component. That's the velocity now in the horizontal direction. So when we go to balance the side-to-side force, that centrifugal force that we're feeling, we'll still have our F lift times sine of phi is equal to our mv squared over r. Well, in the horizontal direction, this time our v is going to be equal to our vg cosine of gamma. And we'll have that it's also going to be equal to r times omega, where this time is r times our course angle, the time derivative of our course angle. So plugging in just like we did before, one of each, we'll end up getting that this is mvg cosine of gamma times psi dot. Right, the r's end up canceling out. Okay, so that's our side to side. Now if we look at our vertical force, previously we just said that F lift cosine of phi, which is our vertical force from our lift, our aerodynamic lift. Previously we'd said that is equal to mg. So if we set that as equal to mg, this is going to be no vertical movement. Okay, so that was if gamma was equal to 0. So when gamma is equal to 0, then we want no vertical movement, which makes sense. Now if we were to move all the way up and have, instead of gamma be 0, have gamma be up here, this is unrealistic. We were wanting to fly straight up, right? We would want no effect from gravity. We want to be going straight up. Now it breaks down. We can't go straight up. But what we can do is now we want to say that our F lift cosine of phi, same as it was before, is equal to mg cosine of gamma. So we just want that we want to cancel out part of gravity. Again, if gamma is equal to 0, we want to cancel it all out. But if it's equal to a non-zero value, we only want to cancel out some of it so that we can be moving. Again, we want to move. This is a change in our height, right, or our altitude. Okay, so we'll do the same as before. We will divide as before. And when we do that, we have our F lift sine of phi over F lift cosine of phi is just going to be equal to, we have now mvg cosine of gamma times the time derivative of our cosine of our heading angle. Yeah. Time derivative of our course angle. And then we have divided by mg cosine of gamma. So those cancel out, and we're left with our tangent of phi is just equal to, we have vg over g times psi dot, or g over vg tangent of phi. Okay, excellent. So we have that nice relationship for our coordinated turn. So in the absence of wind, again, recall that VA is equal to VG, and our heading angle is equal to course angle, which is where we got that first equation, right? And that's an expression commonly seen in the literature. So that's where that coordinated turn comes from. Another thing we can look at is that we have our turning radius, R, is equal to V over omega. So if we're given V and omega, we can determine what R is going to be, right? Recall that V, so that's just our velocity in our horizontal plane. That was just VG times cosine of gamma. And omega in the horizontal plane was just the time derivative of psi, right? So this is psi dot. So we'll put that in there, which was G over VG tangent of phi. So I guess I could leave that there. That was psi over VG horizontal. Okay. And if we write that out, we end up getting this as VG squared all over G times cosine of gamma all over tangent of phi. And for level flight, again, our cosine of gamma is going to be equal to 1 because gamma is equal to 0. We have that R is then equal to just VA. I should say VG. In the absence of wind, we have VA squared all over g times tangent of phi. So here's our radius. If we're allowing wind and being able to go up at a certain direction, here's our radius if we're just doing the planar flight. Okay, so that is our coordinated turn.